Greetings, everyone. My name is Anatoly Tsepelkov, and today I will be your host for tonight, for this morning, whatever. I'm a research scientist at Manaki Research, and also a early career representative of the International Association of Methodological Science of the International Commission of Continental Erosion. And today is my pleasure to host this meeting. We're going to listen to 1.5 or 2 lectures given by Professor Sergey Chalov from Lomonosov Moscow State University and Kristina Prokopeva. We are gonna have 2 Q&A sessions. So after the lecture by Professor Sergey Chalov, you will have an opportunity to ask questions for Sergey. And after, we will have a workshop led by Kristina. And after workshop, you will be able to ask Kristina questions. So there will be about 10 minutes, 15 minutes for every Q&A. So be please mindful about time. As before, you're welcome to ask your questions in YouTube chat. We will copy them and deliver them to lecturers. So without further ado, let me introduce you to and give floor to Sergey Chalov. Please.
Thank you, Anatoly. Thank you, Ekaterina. Good afternoon, good morning, good evening, good night, everyone. It's a big pleasure to proceed today as a lecturer. So I will mostly focus on the more like case studies from what we have done for the last 5 years on remote sensing modeling applications in large rivers sediment transport research. And my examples will cover few rivers, few case studies, mostly within the Russia. And also I will start from methodological points, which will further on more detailedly discussed by Kristina, but after the lecture. So we have now the lecture and the workshop in 2 in 1. And so I would start from the from some general words related to the importance of remote sensing in sediment transport studies. So there are a few things why we start choosing this approach in our research, and it became quite popular over the globe. And in many applications, there is quite abundant vision on the remote sensing applied for sediment transport. And mostly, of course, people focus on the suspended sediments. And actually, I would also focus in the lecture, and Kristina will focus in the workshop on actually these points. How to model the sediment concentrations, suspended sediment concentration in large rivers. And why we do so, there's the lack of observations. That's the main point, that we do not have enough monitoring station, enough monitoring system to cover the knowledge and the variability, the spatial variability, the temporal variability of the sediment concentration in the rivers. This is an example on the screen from the Lena catchment, which is the size of the Lena catchment is more than 2 million square kilometers. And from this vast territory, at the moment we have about 90 gauges sediments transport gets some detailed knowledge. This is one thing. And the second is that the remote sensing is very far from any other traditional methods of any type of the field-based observations. related to the spatial coverage and to the time consumption. So if we look at the traditional methods, or even if we look at some surrogate measurement technologies, we will get the very big limitations in terms of the how many measurements we can get, and each of them, especially if we go to gravimetric studies, which is on the screen, and everybody who knows this approach with filtration, with all these kind of sampling and then processing in the lab, knows that it takes hours with one sample to get the results. So from these two things, we love the remote sensing in sediment transport research. And actually looking at some kind of the rivers where we, so now I jump to the end of my presentation, showing what we can get from remote sensing. We can get the spatial coverage sediment concentration in the large rivers. And this coverage with quite in the resolution of the satellite image, like from meters to dozens of meters, depends on the imagery system we get, will show us the very high spatial discrepancies in the sediment concentrations in different types of the rivers. And as shown on this picture, or as can be seen from this picture, to cover such kind of spatial coverage with the observation, we need thousands of the in situ measurements, which is not reasonable and not even possible with the existing methods, with the existing equipment, even if we get some automatic sensors, the Doppler technologies, and so on. So, and that is the reason to apply the remote sensing, which started in hydrology for the last like 20 years in relation to sediment transport issues. And the first, the most widely used approach, which was chosen by researchers, was the Landsat images, and just general workflow of the Landsat image processing was calculate the sediment transport in the river based on the image, but also that we have archive of the images, and the archive started from the at least 80s. So we got the nice retrospective picture of the sediment transport information in the large rivers. And from this, we can follow to calculate the sediment concentrations in the rivers for the whole periods of the observation by remote sensing imagery. So, and the key point in our applications is that we need to go to the actual the ground truthing data in this regard. So it's not possible to just apply this methodology without ground truthing data. We need observation, but observation are needed for particular very precise calibration images. And it means that anyway, to apply the remote sensing for sediment transport issues, we need the fields data, and field data is done by traditional methods. So this is kind of the picture of what we need with the sediment, with the suspended sediment measurements in the rivers. So there is two types of the analysis which give us enough measurements, enough ground truth measurements of the suspended sediment concentration. It's the optical and gravimetric analysis. And in relation to discharge and velocity profiles, it's is the base to establish what we actually need to set up the calculations of the suspended sediment concentrations from the images. It is the so-called reＦlectance to suspended sediment concentration relationships, or the models, the regional models, which is actually really, in simple words, is the relationship. So on the x-axis, we have the reFlectance, which is goes from the image, which is projected, quality controlled, and link the data from the remote sensing image with the real suspended sediment concentration. So actually we have two things. We have the image, which was done around the dates when the field data was processed, and we have the field data. Then we put it together, and we got this kind of relationship, which we then can move to the other images in our collection. The collaborations of this, the getting of these relationships is the main challenge in all this process. So why it's the main challenge? It's the link, it's the way for the accuracy of the approach. And this way to the accuracy means that we have quite many steps which can either improve or decrease our accuracy. And the accuracy here means that we need quite high level to fit these points between the measured, which is suspended sediment concentration on the y-axis, and the modeled actually data from the image. So for the one, I would use this terminology, the modeled, which means when we recalculate the sediment concentration from the remote sensing, and the measured, it's the ground truth data. So, and this picture shows just one example from one particular river, and I would focus on the papers we publish in this regard, which can be further explained. But this picture shows that if we look at the even one river, but gets different time of the ground truth data and use different respectful images for different periods of the ground truth data, we get different relationships which are changed in the so this data. And by the and on this example, we see that the main driver of the these models between the remote sensing and the sediment concentration is the grain sizes. So if we look at this image, we see that the decrease of the grain sizes, so this is the right arrow on the screen, it's the fining of the material led to led to moving of our fitting equation in this field between the reeffectance and the suspended sediment concentration. And the important thing that if we put all these dots together, it will be also possibility to have the single equation for the whole this data set for this particular river reach. But again, the accuracy increases if we use the seasonal relationships and then apply them for particular hydrological season like floods or low water seasons. And this is quite clearly seen on this screen, how this changed within the particular numbers. Then, of course, I've used a few times already the word accuracy. And if we look on the, we did this place with the accuracy. And of course, this is the main issue again for the whole methodology. There is quite exact estimates of the errors related to these images. This is few things which can be considered in this regard. So different images, different satellites give us different possibilities to get to decrease the errors. So for the Selenga River, there was particular let's say exercises to see what is the real error in terms of the comparison of the measured and modeled sediment concentration, and we fit within the 20% level of the error. And so I don't have time in detail to focus on that. There is quite a lot of written about that in our papers, which I mentioned in the slide. But this is just, let's say, the level of the approach which we evaluate. So another example, and we jump now from the Selenga River, which is the main tributary of Baikal Lake, to the Lena River. Yes, and to the Lena River Delta. It's our favorite one in sediment transport studies. So we have another approach. We compared the modeled the relationship which was get in the field campaign, and the ground truthing was done in one particular year in 2022 field campaign, and move this relationship to the 2024 field campaign, and again compare what is the what will be the accuracy. And in this regard, the mean absolute percentage error we have up to 40%, and this another number is worse than what's mentioned before, but there is also in terms of the absolute values, it's quite nice. But there's quite many things why it is happening. The main one, it's the difference in hydrological conditions between these two, between the modeled period and this period of verification. And the difference in the hydrological situation bring us to this increase of the errors. So again, the seasonality in relationships is very important, but there is at the end hundreds of regional relationships, and we collect them and publish in the textbook, which was just published last. Actually, in Russian language, it's called River Sediments. It's the first textbook since 70s in relation to particular river sediments in Russian post-Soviet scientific landscape. And this is around 200 different regional relationships we put in this database here. And that's their difference is explained by different conditions on particular rivers. But interesting to know that we try to figure out how to improve this. Actually, not just ground truth data is written on the screen, how to improve these models, the remote sensing models. And there are 5 key points which are useful for the researcher to know if you want to use the remote sensing for the sediment transport. And the first is, of course, that the calibration image, so the image from which you get the reflectance intensities and compare with the samples, should be in line in terms of the time. So the minimal time differences, it depends on the hydrological conditions. So if the hydrological conditions are stable, it can be up to a few days, as we get that there can be difference between the data of image and the sampling campaign. But of course, the closer we are, the better. And of course, during the floods, this difference coming in just hours scale. So this is the first thing. Then the shallow and near bunker areas are always an error for remote sensing application, both for calibration and making the relationships and just for application. The resolution of the image, it's the points that one should consider during the whole process. And our experience shows that that's more than 3 pixels is the minimal requirements to apply the satellite image for the particular river channel. So it means that 3 pixels should fit within the root channel borders. And then this regional style of the relationships. So we need to put the different kind of relationship to different river reaches, as far as we have when we go even within one river network, the grain sizes will be changed, the color of the sediments can be changed, and so then the relationship also will be changing. So the better result will be if we apply the particular relationship to the particular river reaches, both in terms of just the spatial and the seasonality gain. And this final requirements is the range of sediment concentration, which I used to the building these relationships. So that's we need, of course, to cover the maximal extended range. So, and this is the key points in application in methodological view. And actually the whole process is very reasonable as far as we get the long-term data from the images. And this is the example from the Lena Delta to show the images which are relevant to use for the study of suspended sediment river reach. So the relevant images means that the cloud coverage is minimal. That's the spatial coverage of the image itself is also cover nicely the studied area. And then for also this experience shows that for each river for each particular river reach, we can get up to 50 and more images from the Landsat collections, which give us the temporal resolution from the 80s of 20th century to the present days. And then the first experiences with all this methodology was done in the GIS systems, and the increase of the let's say images used, and actually the more requests to this data bring us to understanding that we need some kind of the automatization in this regard. And then we moved and see the benefits of the Google Earth Engine as the platform which make the whole process from the images processing and pre-processing and corrections in more or less automatic manner. And this actually I would more with the next few slides announce the workshop, which will be done by Kristina after the lecture. And so the Google Earth Engine was started recently as the platform for all this remote sensing application in riverine research and sediment transport in particular. So the big archives of the data, the coverage, and the possibility to get the ranges which are the bands which are needed for our applications with the particular codes which actually would be able to work today later is the key direction of this GEE application in the sediment transport research. And this is again, it's like announcement of the workshop, but for the lecture, I would then focus on some kind of case studies with the few applications, which will cover actually 2 domains. I would talk about the river, and the example will be the Lena River in its middle course, and then I will talk about the deltas, which were these applications recently. So this is the next, how much, 15 minutes of the talk I would use for these slides. So on the screen, you see actually this middle course of the Lena River, and you see that the sediment concentration is matter of the incredible change, and there is very short scale of temporal resolution, so-called turbulent pulsation in the river system, and of course the ground truthing should be cover how to put all the needed changes in these applications. And the study REACH, which I would further talk about, is located near Yakutsk city. It's the capital of the huge Republic of Yakutia, which almost cover the whole Lena catchment. It's also quite more than 1 million square kilometers the area here, but the Lena River, as seen in the screen, is quite big. It's absolutely applicable for different types of the sensors. We did few studies over there with particular focus on remote sensing application. The most detailed paper was published in Water 2 years ago, and I would more or less bring the examples which were published in this paper. And actually, the main output of these studies was that we cover with the satellite images the 200 kilometers reach. And the images which were in the collections nicely fit the different hydrological seasons. It was like on the left screen, it was floods with maximal discharge observed in the river system. And the river here is the wide floodplain river with the wide valley with the huge territories which are flooded during the high water. And of course, we also focus on the low water conditions when the river is narrowed in the river channel. Anyway, it's an anabranching channel, so there is quite broad system of the flows. But from the even visible analysis of the images, which show the spatial variation of sediment concentration, we get the understanding that the sediment concentration behavior changed a lot between the high water season, which is on the left, and low water season, which is on the right of the screen. And actually, shortly, we see that when the river enters the wide valley, this unconfined river reach, which starts actually somewhere upstream from the Yakutsk, there is a substantial decrease of sediment concentration, which goes from the red color as on the screen to more or less green color. And vice versa, we have the opposite situation during the low water season, the downward increase of the sediment concentrations. And in particular, if we look on more details in some particular reaches, these changes are quite evident, and there's drop of sediment concentration, double drop of sediment concentration on the like 50, 100 kilometers during the floods. And to try to explain it, so there is some signal from hydrology on this in this regard. We try to count suspended sediment budget. Actually, it's the budget, it's suspended sediment change along the river. And this means that we compare the sediment concentration in the upstream of the river and the downstream part of the river, and link it to the discharges. And we see that these visible observations are agreed with the more or less statistical analysis. So when we have the discharge below the, in this case, it was below the 10,000 cubic meters per second, there is downstream increase of the sediment concentration. And if we go to the higher discharges, especially more than 20,000 cubic meters per second, so there is substantially the sediment concentration decreased along the river. And what does it mean? It means that there is the net deposition on the islands, on the floodplains, which are flooded during the during the high water period. And this actually, the main thing, this, let's say, this change, this opposite situations, so which are changed between the seasons of the sediment propagation in the river system, which we actually empirically confirmed from the remote sensing. There are many things beyond this with the hydraulic explanations, and we tried some more specific numerical models to explain this, and it's actually fits well to what we see from the images. But here we talk just about the images, and the information which is just the only source for such kind of data is the remote sensing images. And another thing we discovered is these sediment traps in the small side branches, which store a lot of the suspended sediments. As far as they are quite lengthy, the transport capacity here is very small, and then there is, as also seen on the screen, the sediments which enter these side creeks are deposited, and it's seen in the big sandy bars which are located at this kind of the side bars here. And also, if we compare the samples of the suspended sediments from the upstream part of the such kind of sidebars, side streams, and in the downstream part of this floodplain channels. So we see that there is fining of the materials. So actually, all this coarse material which can be seen in the filters is deposited, and the satellite images, let's say, show this very nicely. Then we try to, as I said, to find some ideas to link it to link these patterns to hydrology.
Unfortunately, we do have some technical issues, so please give us some minutes so we can solve them. Thank you for your patience. We are back online. We'll continue soonish. Sergey, you're free to share your screen.
It was my problem.
Let's not blame somebody.
Sorry for that. So I can continue. I can proceed.
Yes. Do you want me to share your slides or show your slides, or do you?
No, I will continue. Just wait. Nice. So I just disappeared. That's it. Mm-hmm.
Yep, you can continue.
I proceed. Yes,
Yes,
sorry
please.
for that. Yes. Actually, then I would go to the next part of this case studies is I would go from this river scale to the river delta studies, and there will be a few more examples of the construction of the sediments, suspended sediments, changes in the, but in this case in the river deltas. I would start from the Selenga River and its delta, which is belongs to the Baikal Lake tributary. Actually, that was the first detailed approach this Selenga River, where we focus on the sediments, suspended sediment concentration over this distributary delta. There were a few publications on that, with looking on the also vision how this distributary channel affect the hydraulic and then affect the sediment transport conditions. And the sediment transport conditions were again the matter of remote sensing. This map was done and published in the monograph, which was done related to Selenga River and Baikal Lake. This is the map which based on the 45 Landsat images processing for the period from the 1989 to 2015. And each image of the Landsat was recalculated to the suspended sediment concentration, and then the average values were counted for each stream for each particular spot. And so we got this average sediment concentration map, which is also the nice application of the nice approach of the remote sensing data for the river research. And what we can see here, we see that along the delta we get the trend to decrease the suspended sediments in the direction from the delta top to the recipient. All the distributaries like decrease the sediment transport conditions. And it's similar explanation like it was with the previous example from the rivers, that during the floods, we have the inundation of the, and here the very abundant wetlands located here. So they are flooded, and that's decreased the velocities of the stream, that decrease the transport capacity, and the sediments are deposited and stored in the bottom or in the floodplains or in the small lakes or in the marshes around the lake. It's the situation again is quite variable during different seasons. And so if we look on this map, we see that we have quite different situation during the low water season. So this is quite important graph. It's the similar like I showed before for the Lena River. So for the low discharge, there is different situation with the sediment concentration changes along these particular distributaries. And if we go to the high water discharge, so we go in the right direction of this graph, we see that the values go down. It means that the sediment concentration decreased along the river system. And this is because, again, what I mentioned with this inundation and the vegetation. And similar conditions were shown for the Up Angara. It's another tributary of the Lake Baikal, so in the similar conditions. And this was the point which was more or less in nice agreement with the general knowledge about the deltas. That's the traps of the sediments. But then we moved to the northern deltas, to the Arctic, and we got completely different stories when we start looking at the Lena River Delta, then the Kolyma River Delta. And both these deltas give us absolutely new vision what's happening with the sediments, with sediment fate in the river system. And this was discussed during different international things on the Mega Delta program, and in few of our research as well, and published in this Mega Delta book, which was done last year. So this is like a key hint to go for more details that I would mention here. But actually what we get from the Lena Delta in particular, we get that there is the sediments not decreased in the delta, there is not storage of the sediments, there is increase of the sediments. And actually satellites learned us about that. There is a big contradictions with the different like visions or assumptions which done for the deltas as the areas with where sediment should trap, and we see that it's not like that. So this kind of the remote sensing applications was the new step forward of understanding of the processes in the polar permafrost deltas. And actually we were looking what's the reason for that, why the sediments are increasing. So that we counted based on the collection of the archive of the satellite images, we covered the variability, and get that in average during the open water, the suspended sediments downstream increase by more than 2% in the Lena Delta, and particular examples shows these rates of the increase. Then explanation for that was in the direction of course, we do not have such kind of the wetlands around the delta distributaries. We do not have a lot of aquatic vegetation, which also in the southern deltas trap the sediments. But there is some other driver which can increase the sediment concentration. And this driver was found when we analyzed the landform evolution of the delta. There was a particular focus in this analysis of the different factors affecting the sediment concentration for these delta conditions, and with these remote sensing approaches. And we did the map of channel planform change, which was based on the combination of the different time spans of the just planform location of the delta. And we see that in particular reaches, there's quite high values of the bank erosion, which actually affect and in line with the areas where the sediment concentration increased. So that was the clue to answer the question of the sediment fate in the northern deltas, that the ongoing climate change. So if we look more details on this case study, we see that the air temperatures here increased during the last 20, 30 years in quite high rates. This air temperatures increase led to the particular increase of so-called thermal erosion along the river banks, which are covered with the permafrost, a lot of yedomas here. And this influenced the rate of the channel deformation, and this bring the heaps of sediments to the river system. And then we can even follow kind of the relationships between the activity of bank erosion and the sediment concentration in the river system, which explains how the sediment concentration are increased because of the increase of the activity of the bank erosion along the particular banks where the permafrost is the most active degraded. So this was as I showed in the papers, it's quite detailed discussing in this regard, but it's of course very let's say the results which was possible to get only based on the satellite images application, as far as previously these especially northern deltas were covered just with some irregular grab samples and which were not able to answer the question of the sediment fates in the deltas. So this is only thanks to the remote sensing. And the last point I would mention is then we compared the northern deltas, the Lena and Kolyma, and the southern Selenga and Apangara, located more or less in one spatial coverage in the Siberia, in the northern part of Siberia and in the southern parts of Siberia. And we published this in the paper in the remote sensing application, in the remote sensing in 2021. And this was the final graph of this paper, which showed that the southern deltas tend to be a depositional system, whereas the northern one tend to be the erosional, which transfer the sediments or even adds additional amounts of the sediments to the river flow, which then deliver to the recipient. Yes. Then, as agreed, I finish with this 40 minutes presentation. Thank you, those who attended this lecture. Sorry for technical break. And
thank you,
yes.
Sergey. No worries. I think no matter the technical issues, we all enjoyed your talk. We do already have some questions in YouTube chat. Where currently you can find them in our Zoom chat. To other listeners, please don't be shy. Ask your questions. Shoot them. We will discuss. So the first question was from Alessandro Catapan. Are the delta SSC variations in time, space, water discharge, or something else?
Yes, thanks. So the first thing, yes, it's the discharge is the main driver, but that's not elsewhere. So if we go to the deltas which have the wide some wetlands which are flooded, then the discharge is the dominant driver, because when the high water conditions bring water to these wetlands, there is the main influence and main impacts on the sediments which just captured and stored in these flooded areas. But related to time and space, then if it's the matter of discharge, then yes, it's the matter of time, because discharge as the driver is the time dependent variable. And related to space, also yes, space is important. And the last example which I showed with this variation between the northern and southern deltas shows us that of course the deltas located in different environments are also different, and in terms of the how they influence the sediments. And then also yes, space, time, discharge, and other drivers are the dominant.
Thank you. Another question from Vladimir Voinov, and it kind of more or less the same question I'm curious about. So if you don't mind, I will rephrase the Vladimir question a bit. So you showed us that there is a decrease in surface suspended sediment concentration in Lena Delta from downstream. So do you account for uncertainty in your estimations based on the satellite imageries? Because like 2.3% is quite a small decrease. Don't you think that this is maybe inside the confidence interval of estimation of suspended sediment concentrations in different parts of the delta?
There are many steps to talk about the uncertainty and the accuracy, and so I mentioned the uncertainties related to actually the approach itself when we apply, when we calculate the sediment concentration from the images. It is the first step of the uncertainties, and this was quite abundantly studied in our applications. And related to these estimates for the Lena and 2.4% increase, this is based on the data set of the images, and there is inside this data set we have the over 70 let's say sediment concentration maps which were built for different hydrological conditions, and from that I would say that this it's like a statistically significant estimate as far as the number goes from the processing the just quite big data set, and here we have the conclusion, which is rely on the different situation, different conditions, something like that.
Okay, thank you. One more question from YouTube. How to find the water discharge values of each river? Do you have any suggestions?
We have two things how to. There is of course the monitoring stations, and in our study we mostly focus when we compare the sediment concentration with discharge from the monitoring which is done on these particular rivers, or there is quite also nice possibilities from reanalysis to count the daily discharge for the rivers, but of course the monitoring data is the most reasonable one.
Okay, thank you. And I think maybe the last question, and I think you should decide should you answer it or not, or maybe this question should be passed to Kristina. So Landsat and Sentinel-2 images has different spatial and spectral resolutions. The question is, how do you harmonize these datasets in Google Earth Engine to ensure consistency and suspended sediment concentration time series estimations?
I would say that it's, I would not put this point like that we need to harmonize the data sets. So each satellite each satellite imagery is processed independently, and then we analytically work with the results which goes from the processed images in autonomous way. And the data itself can be similar. For example, if we count for the particular river reaches the sediment concentration change, then we can compare this data when we put it even taken from the different satellite images. Technical things of the GEE application, yes, I think it can be maybe better talks on the next part of our lecture workshop. Yes, thanks.
Thank you, Sergey. So I think I'm mindful about time. So I'm mindful about time, and I think it is time to proceed with Kristina's workshop. So thank you very much, Sergey, on behalf of all our listeners.
Thank you for your questions. Thank you for convening this session. And yes, good luck, Kristina.
Kristina, you're welcome. Let me first introduce you. Now we will have a lecture workshop by Kristina Prokopeva. She's currently a PhD student at Lomonosov Moscow State University, Faculty of Geography. And she will unleash us uncover some practical applications of Google Earth Engine for suspended sediment estimations in the cloud. So please, Kristina, the floor is yours. You're welcome to share your screen.
Thank you. Thank you. Good morning, good afternoon, good evening. I'm very glad to welcome you to our School for Young Scientists. And I hope that the lectures and workshop we have prepared for you will help you in your future investigations. Let me introduce myself. My name is Kristina Prokopeva, and I'm junior researcher of the Makeyev Laboratory of Soil Erosion and River Channel Processes of Moscow State University. And today I will be talking about an exciting and powerful tool, Google Earth Engine, and how we can use this application in modeling suspended sediment concentration from your home or from your work desk, and just applying remote sensing data sets. When we first started using remote sensing data set, we had to do everything manually. This took a lot of time as we had to download terabytes of images and spend hours pre-processing them. And after all of these steps, we were finally able to see the results in the form of colorful pictures of suspended sediment distribution. And how much easier life became after we learned how to use the Google Earth Engine platform to study suspended sediment transport. First, let's briefly introduce Google Earth Engine. This is a cloud-based platform.
Can you please go in the full screen mode? Start the slideshow.
Oh, sorry.
Thank you.
Yes. This is a cloud-based platform for planetary scale geospatial analysis that brings Google massive computational capabilities to process large amounts of geospatial data in a scalable and efficient manner. And it provides access to a vast collection of satellite images, remote sensing data, and geospatial data sets that can be analyzed directly on the cloud. And the most important feature of this platform is free accessibility for everyone. You simply need to make a few small improvements to your programming skills using the JavaScript language or Python. And the second aspect is a planetary scale, which implies the ability to explore rivers from their headwaters to their estuaries on every continent. And the third is temporal resolution. The platform provides near real-time satellite images So we can monitor suspended sediment dynamics at various time scales, whether we are interested in seasonal trends or some post-storm effects or in long-term change in transport. And the last is free cloud processing with built-in functions. And you don't need to download terabytes of datasets and powerful personal computing resources. Just open the website and start writing your own code. How does Google Earth Engine help us with the suspended sediment concentration model? The challenge is that monitoring and modeling suspended sediment concentration over large areas is traditionally time-consuming and resource-intensive. And however, with the advent of Google Earth Engine, we can significantly enhance our ability to model suspended sediment concentration on a large scale using satellite imagery. And one of the most common methods is to use the reflectance of light in certain wavelengths to estimate suspended sediment concentration levels. And for example, the presence of suspended sediment matter cause changes in the color of water, and particularly in the visible and near infrared parts of the spectrum. And by analyzing these changes over time, we can generate high resolution maps and track its variation across different regions and seasons. And certainly, we must conduct in situ measurements in order to calibrate your regional model, which we use to compute the images and the reflectance of the images and related to the concentration, in situ concentrations in milligrams per liter, for example. And it will be advantageous if the date of in situ measurements coincided with the date of satellite imagery. And it will be helpful if you could obtain an additional independent measurements to validate your results. And now a lot of regional algorithms were developed, and if you're interested, we can share with you all of these equations. Just write me email. Yes. Let me give you one example how Google Earth Engine has been applied in a real issue. And here is a step-by-step guide to process satellite imagery in Google Earth Engine to calculate suspended sediment concentrations. For this process, we will be using remote sensing data sets such as from Landsat, Sentinel to modest satellites. And I think that you know that all of these data sets vary by spatial resolution, by time frequency. Yes, and in our example, we will use Landsat 8 satellite and certain spectral band, red band, and referlectance in red band. Yes. Now we will open Google Earth Engine to write the code. I guess that you have already set up a Google Earth Engine account. And for that, please go to the sign up page and follow the instruction to create an account. And then you need to access the code editor to start writing and running scripts. At the first, we need to choose satellite data. This is the second line. You know that we can use a range of satellite data sets. Our example is based on the Landsat images. And we will use images which already calibrated, and these data sets provide us values on the top of the atmosphere reeffectance. Then you create the layer, create the name of this layer, and then you can filter all the database by the date, by the metadata, by the bounds. Also, you can apply some filters which about cloud cover, but I prefer and I suggest to check all of available images because of cloud cover. Is one is disadvantages of remote sensing, and for instance, you can have more than 100 images per season for your area of interest, and only 10 out of 100 will be suitable because 50% of your image will be covered by cloud, but the rest 50% of image will match with your area of interest. And for that, I prefer automatic Google Earth Engine platform, but I check all the images. Yes. And also, please keep in mind that Landsat provides different types of the data sets. It can be raw data sets, raw images, images with radiometrically, which already radiometrically corrected with the top of the atmosphere value or bottom of the atmosphere values. And for example, about cloud cover, for Sentinel-2, you can also use QA60 band to mask out clouds because they already have this mask. But I think that it's also unclear because you can't delete the shadow from these clouds. Then we need to define area of the interest. You can either manually draw it tools by using drawing tools in Google Earth Engine. You can find it here. You can do it using figure or by points. Also, you can download your own shapefile. Just make sure about coordinate systems. Yes. Then you can setting the characteristics and how your image will display on this window. Yes, just we can start our first probably 20 lines and how it will look if we will add there our first images, which will present us the images on the top of the atmosphere. Yes, these two images for the Lena River Delta for the 13th of July 2021. Also, you can combine different bands. For example, there we see combination of the red, green, and blue bands. If we will change, for example, this two, the images and how it will display also change. Yes. And you can choose different combination, and it's as you wish. I would like to continue with natural colors. And I'm sure that the most important part of processing the satellite data is atmospheric correction. And atmospheric correction aims to eliminate the effects of haze, cloud, hazes, aerosols, and help to get accurate spectral description of Earth and water surface. And for that, we choose the IAHS-ICCE method. This method includes the uncertainty information from different data sources. It takes advantage of high temporal resolution of modest observation to get the directional reflectance distribution function. And also it uses the Copernicus Atmospheric Monitor service from European Center for Medium Range Water Forecast. And these parts of atmospheric correction provide us the prior information of the near real-time atmospheric condition. And it helps us to get optimal estimation of atmospheric parameters. And the main idea of this correction is performed top of the atmosphere values, top of the atmosphere reflectance to the bottom of the atmosphere reflectance. And for that, we just need to write this one line and then apply CIC method to the new layer, where you will use your previous layer, top of the atmosphere, will perform to the bottom of the atmosphere. And then we can add these layers to the window. And now you can see how a picture should be brighter. Yes, because now we delete all effects of the atmosphere and aerosols, haze. Yes. And also there I use my first color scale that I invent for the first layer, where there are combination for the red, green, and blue bands. Yes, works. Then we need we already have reflectance value in the bottom of the atmosphere, and then we need to recalculate these values to the suspended sediment concentration values. And for that, and typically remote models use visible and near infrared bands which are sensitive to the amount of suspended particles in the water. And there are a lot of combination to develop your own equation. And for instance, for the Lena River Delta, we tried to combine different spectrums to model development, but the highest correlation between in situ measurements and reflectance in the red band were higher than in another. And the type of this regression is linear. You already seen this picture. Yes, but for different rivers and different type of sediments, the equation type can vary. And keep in mind that turbid water equation could be exponential or multi-regressional. Yes, and there we apply our equation for the Lena River Delta. And the red, this is the red band, and you need to clarify that the red band, this is band 4 for the Landsat 8 satellite. For Landsat 7, it will be band 3. For Sentinel 2, it will be also band 4. Yes, and if we run the code, it will be looks like a lot of colors on the Lena River Delta. We need to wait. I think you already see the differences between concentration in the river and the sea, and how it's vary by colors and also by values. And of course, you can use inspector on the map to see the values. And this window provides information for all layers which you're using your work. For example, there you can compare reflectance value for the red band on the top of the atmosphere. And what happened after atmospheric correction application for these layers, the value decrease because we delete all reflections and scattering by atmosphere. Yes. Now it looks like everything is water, but the land is played as a very turbid water. If we click on the sand, for example, and we can see the values of suspended sediment concentration on this. 3030. It's lower than Yellow River. And to exclude this misunderstanding, we should extract only water surface. And I'm sure that each of us has faced this task at some point. For water surface identification, many indexes have been developed. And now we will use normalized difference water indexes. And on the slide, you can see another indexes, and you can try every index and then compare the result and use the best for your river. in DBI, indexes is used to highlight open water, features, and it's based on the combination of green band 3 and near infrared band 4. This combination allows to detect subtle changes in water content of water bodies. After running our code, we see that the water surface more brighter than land or sand areas. And also you can, then we need to extract our suspended sediment concentration layer by this new layer of DBI. For that, 66 and 67 lines, there you can choose the range for cutting your NDVI layer. Yes, and then we get the final result of suspended sediment concentration layer and maps. Also there we can add satellite images. It will improve picture. Yes, this is our final result, but I think we don't just create pictures to look at. We need data from these amazing views, and for instance, calculate mean suspended sediment concentration on a specific section of the river. And for that, we should create, for example, I create shapes for the top of the delta and the different branches, and then suspended sediment concentration will be calculated into these shapes. Yes, and the result you can see on the console. There are calculated concentration for each parts of the images. And then you can download all of images, all values at your Google Drive, and then use it as your wish. I think that's all. And in conclusion, I would like to say that Google Earth Engine is revolutionizing the way we approach monitoring, suspended sediment monitoring, and its application to model sediment in sport. And this is only just one example of its vast potential, and with its global scale, rapid processing power, and integration with the in situ data, Google Earth Engine allows us to tackle with challenges which related with water quality, climate change impact, and anthropogenic impact also. Thank you for your attention, and I will be happy to answer. for your questions.
Thank you, Kristina. This is really helpful. Please ask your questions in YouTube chat. While our participants are typing their great questions, may I ask you one question from myself? I'm curious about the atmospheric correction algorithm you applied. So this SIAC one.
Yes.
Why did you choose this algorithm?
Okay.
Because as far as I know, it's a Bayesian one. It can be a bit overcomplicated for this task.
For atmospheric correction, we need to measure all of reflection and scattering by water in situ, and then recalculate top of the atmosphere images according our measurements. But we haven't these measurements, and for that we need to apply data sets where these parameters already were measured. And for that, we use Copernicus data sets, which provide less information about atmospheric condition and modest satellites with high frequency of the data. And CAHC methods, it's already applied in Google Earth Engine, and according to our verifications, it provides a clear result. It's provide a clear result. Yes, that's all.
Okay, fair enough. Yeah, thank you. Okay, so this is good question from Nilay. So can you provide any way how can I get SSC formula, so suspended sediment concentration equation, for my own region? Is there any generalized equations at all? So I mean, I think means that Nilay means that is there any formulas which can be used no matter what the region is, or yeah.
Okay, I sure that every river should have their own equation, because the sediment and sediment size, sediment color vary from different rivers. Of course, probably yes, generalization is possible. But for example, we try to use plenty of equations, for example, for the Kamchatka Peninsula, but it doesn't work. And I'm sure that every river, one equation. You can try to generalize, but I prefer to use my equation because I rely on my results, on my measurements, my in situ measurements.
Thank you. I can see a lot of questions about the code availability. Dear participants, we will send you an email shortly after our lecture with all information regarding the code and how to apply it. Please just be patient. So I think our time is up. So thank you very much, Kristina, for your presentation.
Yes, also I think that we can send for participants the useful links or guides, tutorials, if you're interested to apply a Google Earth Engine in your research. And these links will help you to start to write your own code and solve your task. Thank
Sure,
you.
I think it's a great idea. Thank you. So thank you very much. I think I will finish our meeting for today, and I just want to thank you all for coming and for asking some great questions. And I also want to thank all our lecturers, Sergey and Kristina, for giving so great presentations, no matter the technical issues. I just want to warn you that tomorrow we will start 1 hour earlier, and our speaker for tomorrow will be Dr. Alexander Osetchev with his talk about the satellite monitoring and numerical modeling of riverborne sediments in the coastal sea. So we're actually switching from rivers to the sea. I think it sounds really interesting, and I'm really looking to see you tomorrow. So thank you very much, and goodbye.